Hey guys, welcome back to Calculus Universalis. Today we're going to be going over trapezoidal rule and Riemann sums. Alright, let's head into it. So, a limit of a Riemann sum is an approximation, but as the number of rectangles will increase, approximation gets more accurate. That's basically the concept that we're going to be going over today. So definite integral is defined as the limit of the Riemann sum. So you have your integral dx is the limit as n goes to infinity of your Riemann sum. Sum of n equals 1 f of x to the n, right, times delta x. So your infinite limit, the infinite number of rectangles, defines your definite integral, which is very helpful. And it makes sense because the more infinitely thin slices you put in here, you have big rectangle, but if you put an infinite number of rectangles, you have the total area. So that's what this is right here. So the trapezoidal rule is, instead of using rectangles, what if we connect the tops of each interval with a line to form trapezoids? Something like this. Like that. And this gives us a way more accurate than midpoint, left, or right Riemann sums. So our formula looks something like this. You can write it down in your notebook. Okay. If the interval a and b is divided into n equal parts of width x, then it'll be something like this. A to b, f of x dx equals delta x over 2 times your f of x naught plus 2 f of x 1, oh my gosh, and then 2 times the rest. So let's dive into our example. This might be confusing. Example number 1. You're given values of f of x at x equals 0, 2, 4, and 6. F of 0 equals 3, f of 2 equals 5, f of 4 equals 6, and f of 6 equals 7. Use the trapezoidal rule with 3 sub-intervals. Let's say delta x equals 2, which it does. Apply this formula. Prox equals 2 over 2 times 3 plus 2 times 5 plus 2 times 6 plus 7, which equals 32. Estimated area 32 units squared. Second example. Suppose you used both trapezoidal and midpoint approximations for the same function. If the midpoint gave 30, the trapezoidal gave 32, which is more accurate. If the function is concave up, trapezoids overestimate. Midpoint underestimates, so the true value is somewhere in between. Use both to get a tighter estimate. Example number 3. Limit of the Riemann sum. Let's write a Riemann sum that estimates integral from 1 to 5 x squared dx with n rectangles and right endpoints. Delta x equals 5 minus 1 over n equals 4 over n. The right endpoint for ith subinterval x to the I equals 1 plus I plus 4 over n, you're going to have n sum I equals 1 plus 4i over n squared times 4 over n. This is a Riemann sum, and in the limit, it becomes the definite integral. Okay, let's summarize what we learned today. Riemann sums approximate area using rectangles. The definite integral is the limit of these sums. The trapezoidal rule uses trapezoids to improve accuracy. And the area equals the formula that we mentioned. You need to know how to use this with tables and graphs. And on the AP exam, expect to estimate an integral using table values and identify over or underestimation. You can practice trying to use the trapezoidal rule to approximate integrals, writing a Riemann sum that approximates certain integrals with right endpoints in an integral and rectangles, and then compare estimates. Next up, we're going to learn definite integrals and their properties, including how to evaluate them exactly and use their algebraic rules. See you in